So let's move on to angular motion dynamics, which covers torque, energy in rotational motion, and angular momentum. As we have seen in angular motion kinematics, many equations in angular motion follow the same form as in the linear motion equations. All you need to do is just replace the linear motion variables with their angular motion counterparts, and you have your equation for angular motion. For example, in kinematics, all you need to do is remember your linear motion kinematics, replace x with theta, v with omega, and a with alpha. You have your angular motion kinematics equations. The same can also be said with angular dynamics. All you need to do is just remember your equations for linear motion dynamics and just replace the variables with their angular motion counterparts. For example, you have torque, the rotational counterpart of force. You'll recall that net force is equal to mass times acceleration. F net is equal to ma. Net torque is equal to I alpha. Work, power, and rotational kinetic energy, as you can see, they also follow the same form as the linear motion equations. Conservation of energy still considers kinetic energy, potential energy, and external work done. Initial energy is still equal to final energy. The total energy is constant. But now, not only do we have linear kinetic energy, we must also consider rotational kinetic energy. Angular momentum, conservation of angular momentum, still follow the same equation forms as in the linear momentum equations. Linear momentum, P is equal to mv. Linear momentum is equal to mass times velocity. Angular momentum is equal to moment of inertia times angular velocity. L is equal to I omega. In addition to net torque is equal to I alpha, we may also determine torque by looking at how the force is applied on the object with regards to the pivot point. Torque may be seen as the ability of a force to rotate an object about a pivot point. Torque is equal to plus minus Fd, where D is called the lever arm or moment arm of the force. It is the perpendicular distance from the line of the force to the pivot point. And net torque is the summation of the individual torque applied or experienced by the object. Next, we have the second condition of equilibrium. In linear motion, we covered the first condition of equilibrium. Net force is equal to 0. For rotational or angular motion, we have the second condition of equilibrium. Net torque is equal to 0. That is to say, angular acceleration is 0. A system in a state of equilibrium is characterized by constant angular velocity. If the angular velocity is constant at 0, the system is said to be in static equilibrium. And if the angular velocity is constant at a non-zero value, the system is said to be undergoing uniform circular motion. If the system is not in a state of equilibrium, then it is an accelerating system. The net torque is equal to I alpha. So depending on the state of the system, the net torque is either zero, the system is in equilibrium state, and if the system is accelerating, net torque is equal to I alpha. For a system to be in a state of total equilibrium, it must satisfy both the first and second conditions of equilibrium. If it only satisfies the first condition, then the system is in equilibrium only in linear motion. If the system is it satisfies only the second condition of equilibrium, then the system is only in equilibrium only in rotational motion. And that's pretty much it for angular dynamics. As you can see, equations are relatively easy to remember, as for the most part, most equations in angular motion follows the same equation form as in linear motion.